When a massive star dies, it doesn't fade quietly. It explodes with a power so great it can outshine an entire galaxy. These are supernovae, the engines of creation and destruction in the universe. Today we'll uncover the science behind these cosmic blasts. If you enjoy this journey, please like, subscribe, share, and leave a comment with your thoughts. Thank you for watching. Now let's begin. A star begins its life as a vast cloud of gas and dust. Gravity slowly pulls this matter together, causing it to collapse and heat up at the center. As the central temperature and pressure rise, nuclear fusion ignites, and hydrogen nuclei combine to form helium. The energy released from fusion pushes outward, balancing the inward pull of gravity. This balance defines the long and stable phase of a star's life known as the main sequence. The exact way a star lives and dies depends on its mass. Stars of small mass, such as those comparable to the Sun, live for billions of years, slowly fusing hydrogen into helium, and then helium into heavier elements like carbon. When the fuel is exhausted, these smaller stars expand into red giants and shed their outer layers, gently leaving behind a dense remnant called a white dwarf. Such stars end quietly and do not produce the catastrophic explosions known as supernovae. In contrast, stars that begin their lives with far more mass take a different path. A massive star fuses heavier and heavier elements in its core over a much shorter timescale. It passes from hydrogen to helium, then to carbon-oxygen, neon-silicon, and finally iron. Each successive stage burns more quickly. Hydrogen may last millions of years, but silicon burning to iron can occur in just a few days. The reason this progression eventually halts lies in the nature of iron itself. Fusion of elements lighter than iron releases energy, while fusion of iron or heavier elements requires more energy than it produces. When the core becomes dominated by iron, the star cannot gain further energy from nuclear reactions. Without an energy source to push outward, gravity takes control. The immense weight of the outer layers presses inward, and the star begins a catastrophic collapse. For a star with at least 8 to 10 times the mass of the Sun, this collapse happens rapidly within seconds. The core is squeezed to densities similar to an atomic nucleus, and the protons and electrons are forced together into neutrons, releasing a flood of neutrinos. These tiny particles carry away enormous amounts of energy. Meanwhile, the sudden stop of the collapse creates a shock wave. If conditions allow, the shock is revived by neutrino interactions, and it blasts the outer layers of the star into space. This event is what observers recognize as a core collapse supernova. The collapse is a violent endpoint to the steady life of a massive star, transforming it into either a neutron star or a black hole depending on how much mass remains. Stars of lower mass that end as white dwarfs follow a quieter road, but under certain circumstances they too can explode. If a white dwarf is part of a binary system and draws matter from a companion star, its mass may increase. As it nears a critical limit known as the Chandrasekhar mass, the pressure of degenerate electrons that normally supports the star can no longer resist the pull of gravity. The core ignites in runaway thermonuclear reactions, consuming carbon and oxygen in a matter of seconds. The entire star is unbound, producing what astronomers call a Type Ia supernova. Unlike the collapse of a massive star, this explosion is powered by thermonuclear energy, rather than gravitational collapse. Both pathways lead to similar outcomes in appearance, an immense release of light and energy outshining entire galaxies for a short time. The distinction between quiet and explosive endings emphasizes the role of mass in stellar life cycles. A star only a few times more massive than the Sun can alter the chemistry of a galaxy by enriching space with heavy elements through its explosive death. A star, similar to the Sun in contrast, contributes through slower processes such as stellar winds and planetary nebulae. Scientists measure these outcomes through careful observation of stellar populations. In galaxies rich with young, massive stars, core collapse supernovae occur frequently. In galaxies dominated by older stars, thermonuclear explosions from white dwarfs become more common. This difference explains why surveys of distant galaxies reveal different kinds of explosions depending on the age and composition of the stellar environment. The stages leading to a supernova are not always visible directly, but astronomers study them through indirect evidence. Red supergiants, luminous stars with masses above the critical threshold, are observed in nearby galaxies. These stars are unstable, shedding material through strong stellar winds. Blue supergiants and Wolf-Rayet stars stripped of their outer layers represent later phases of massive star evolution. These observations confirm that such stars are among the progenitors of future supernovae. In the case of white dwarfs, accreting systems such as novae and recurrent novae provide clues to the build-up toward instability. While not every white dwarf in a binary will reach explosion, these systems highlight the delicate balance that determines stellar fates. In essence, the possibility of a supernova rests on the competition between two forces: the inward pull of gravity and the outward push of energy from nuclear reactions or from the pressure of degenerate matter. When the outward push fails, collapse or runaway fusion begins. The difference between a quiet fading star and a cosmic detonation lies in how and when this balance breaks. Understanding these processes required centuries of observation and decades of theoretical work. Early astronomers could only record the sudden appearance of bright new stars without knowing their origin. Today, detailed models of stellar interiors and long-term surveys of star-forming regions allow scientists to trace the pathways toward these explosive ends. Computer simulations follow the progress of fusion reactions, the growth of ion cores, and the dynamics of collapsing matter. Observations of nearby galaxies confirm these predictions by revealing massive stars in late stages of life. The calm flow of stellar life cycles from birth in a molecular cloud to death in collapse or explosion is a process that repeats across billions of stars. Yet only a small fraction will end in the brief brilliance of a supernova. The rarity makes each event a valuable source of information. Every time a supernova appears, it allows scientists to test models of stellar evolution, nuclear physics and cosmic enrichment. These events link the quiet lives of stars to the broader cycles of galaxies, but at their foundation they are the natural consequence of the physics of matter under extreme pressure and temperature. The story begins with the simple fusion of hydrogen and ends for some stars in a sudden and luminous death. When a massive star approaches the final stages of its life, the balance that has kept it stable begins to unravel. For millions of years, fusion of lighter elements has supplied energy to hold back gravity. Hydrogen fuses into helium, helium into carbon and oxygen, and in turn into heavier elements until iron dominates the core. At this stage, fusion ceases to provide energy, because combining ion nuclei does not release power, but instead consumes it. The star has no further fuel to resist gravity. The inward pull takes over and the core collapses in seconds. The collapse is rapid and unstoppable, driving densities and pressures to extraordinary levels. As the core shrinks, electrons and protons are squeezed together to form neutrons, a process known as electron capture. Each reaction produces a neutrino, a particle so light and weakly interacting that it escapes almost freely. A vast flood of neutrinos streams outward from the collapsing core. In just a few seconds, more energy leaves the star as neutrinos than all the light radiated during its previous lifetime. These neutrinos mark the physical heart of the supernova mechanism, even though they are invisible to the human eye. The collapse does not continue indefinitely. When the matter in the core reaches densities similar to that of atomic nuclei, the repulsive component of the strong nuclear force halts the infall. The inner core stiffens suddenly and the outer core crashes into it. This rebound generates a shock wave that attempts to push outward against the weight of the still collapsing layers. At first, the shock stalls. Energy is drained from it by the dissociation of iron nuclei into free protons and neutrons, and by the ongoing flood of neutrinos escaping the core. The stalled shock presents a puzzle. How can the explosion succeed if the initial rebound loses its strength? This is one of the central challenges in the physics of core collapse supernovae. Modern models suggest that neutrinos themselves play a critical role in reviving the shock. While most neutrinos pass through matter unimpeded, the density near the core is so high that a fraction of them deposit energy in the layers just behind the shock. This heating creates turbulence and convection, stirring the matter and giving the shock new momentum. If conditions are favourable, the shock is re-energized, bursts outward, and carries the outer layers of the star into space. The outward moving blast tears through the envelope of the star in seconds, accelerating matter to thousands of kilometers per second. As it races outward, it heats the stellar material to temperatures of billions of degrees, causing nuclear reactions that form new elements. The escaping shock eventually reaches the surface of the star. At that instant, called shock breakout, a sudden flash of ultraviolet and X-ray radiation bursts into space. Observers with sensitive instruments can catch this fleeting signal, which lasts only minutes to hours depending on the size of the star. After this flash, the expanding debris becomes visible as the brightening supernova light curve. The outcome of the collapse depends on the mass of the core. If the remaining mass after the explosion is less than about 3 times that of the Sun, the neutrons hold together as a stable object known as a neutron star. If the mass is greater, not even neutron pressure can withstand gravity, and the core continues collapsing into a black hole. The precise threshold is uncertain and depends on rotation magnetic fields and details of nuclear physics. In either case, the event marks the irreversible transformation of the star's core into one of the densest objects in the universe. Computer simulations of core collapse supernovae remain an area of active research. The physics involves a combination of nuclear interactions, fluid dynamics, neutrino transport, and magnetic effects. Different models explore how rotation and strong magnetic fields might contribute. In some scenarios, jets of material powered by rotation and magnetic energy help drive the explosion. These so-called magnetorotational supernovae may explain certain unusually energetic events. The details remain under investigation, but the central picture is consistent. The collapse of a massive core produces a shock neutrinos transfer energy, and the outer layers are expelled in a bright explosion. The timescales involved highlight the contrast between a star's stable life and its sudden death. The fusion of hydrogen in the core of a massive star may last 10 million years, while the collapse itself takes less than a second. Within that instant, the fate of the star is decided. The observable glow that follows can last months, but the underlying transformation is nearly instantaneous. Evidence for these processes comes not only from theoretical models, but also from observed signals. In 1987, neutrinos from a supernova in the Large Magellanic Cloud were detected by underground detectors in Japan and the United States. Only a handful of neutrinos were recorded, yet they confirmed decades of predictions that core collapse floods space with these particles. The arrival of neutrinos before the visible light reached Earth showed that they escape directly from the core, while photons emerge only after the shock has broken through the stellar envelope. This detection remains one of the most direct confirmations of the role neutrinos play in supernovae. Astronomers also study the distribution of supernova remnants to infer the outcomes of collapse. Neutron stars with powerful magnetic fields called magnetars and rapidly rotating pulsars are observed at the centers of remnants. In some cases, no compact object is visible, suggesting that a black hole may have formed. These observations link the theoretical picture of core collapse to real astrophysical objects. Each case adds evidence to the overall framework, even as details remain under refinement. The physics of core collapse connects stellar astrophysics to particle physics and nuclear matter. Conditions inside a collapsing core are impossible to reproduce on Earth. The density exceeds that of atomic nuclei, the temperature climbs to billions of degrees, and neutrino interactions dominate the dynamics. Studying supernova therefore provides insight into matter under extreme conditions. Laboratory experiments with particle accelerators and nuclear reactors offer partial information, but only the cosmos produces natural laboratories of such intensity. Supernovae thus serve as both astrophysical events and as windows into fundamental physics. The calm picture of a star shining steadily for millions of years ends abruptly in collapse. Gravity unchecked by fusion compresses the core until the very structure of matter is altered. The outward shock powered by neutrinos decides whether the star explodes or vanishes silently into a black hole. Observations of remnants, neutrino signals, and light curves confirm this general process, while simulations refine the details. The collapse of a massive star demonstrates how the life of matter is governed by physical laws acting step by step, from fusion to failure and finally to explosion. While the collapse of massive stars dominates the discussion of supernovae, there is another pathway that leads to stellar explosion. This route involves stars of lower mass that end their normal evolution as white dwarfs. A white dwarf forms when a star similar in mass to the Sun exhausts its fuel and sheds its outer layers, leaving behind a dense core about the size of Earth. The white dwarf is supported not by ongoing nuclear fusion, but by electron degeneracy pressure, a quantum mechanical effect that resists further compression. By itself, a white dwarf is stable and slowly cools over billions of years. However, in a binary system where a white dwarf orbits with another star, new conditions can arise that destabilize it. If the companion star evolves and overflows its outer layers, or if the two stars orbit closely enough for mass transfer, the white dwarf can accrete fresh material. As matter builds on its surface, pressure and temperature rise. In some cases, a runaway fusion of hydrogen on the surface produces a nova, a relatively small outburst that does not disrupt the star. But if the accretion continues and the white dwarf grows in mass toward a threshold known as the Chandrasekhar limit, about 1.4 times the mass of the Sun, conditions become critical. At this point, electron degeneracy pressure can no longer resist gravity. Instead of collapsing quietly into a neutron star, the carbon and oxygen in the core ignite in uncontrolled fusion. Unlike in normal stellar cores where fusion adjusts smoothly to changes in temperature and pressure, the degenerate matter inside a white dwarf does not regulate itself. When fusion starts, the pressure does not increase to halt it, so the reactions race unchecked. Within seconds, the carbon and oxygen ignite throughout the star in a chain reaction. The result is a thermonuclear runaway that unbinds the star entirely. This explosion is known as a Type Ia supernova, in contrast to core collapse, which leaves behind a neutron star or black hole. A Type Ia supernova completely disrupts the white dwarf, leaving no remnant. The exact mechanism of ignition remains under study. One model suggests that the fusion begins as a subsonic flame called a deflagration that spreads through the star. In some cases, the flame may transition into a detonation, a supersonic front that consumes the remaining fuel in milliseconds. The details of this transition determine how much nickel-56, a radioactive isotope, is synthesized in the explosion. The decay of nickel-56 to cobalt-56 and then to iron-56 powers the light curve of a Type Ia event. The brightness and shape of this curve are remarkably uniform among different explosions, which is why Type Ia supernovae serve as important distance markers in cosmology. Another possible path to thermonuclear explosion is the merger of two white dwarfs. If two stars of comparable mass spiral together due to gravitational radiation, they eventually collide and coalesce. The violent compression may ignite fusion before or during the merger. These double degenerate scenarios provide an alternative to steady accretion from a companion. Observations suggest that both single degenerate and double degenerate channels may operate in nature. The relative frequency of each pathway is a topic of active research, combining surveys of supernovae with population models of binary stars. What distinguishes Type I supernovae observationally is the absence of hydrogen lines in their spectra. Because the progenitor is a stripped white dwarf, there is no envelope of hydrogen to produce such features. Instead, their spectra show strong lines of silicon early in the explosion and later reveal iron group elements. These features allow astronomers to classify them even in distant galaxies. The uniformity of their brightness, once corrected for small differences in light curve shape, makes them powerful standard candles. In the late 20th century, observations of Type Ia supernovae in distant galaxies revealed that the expansion of the universe is accelerating a discovery that led to the concept of dark energy. Despite their use as tools in cosmology, many questions about Type Ia progenitors remain unresolved. Direct searches for companion stars in remnants sometimes fail to find evidence of a surviving donor, suggesting that mergers may play a larger role. On the other hand, some systems show signs of circumstellar material that could indicate mass transfer. The diversity of light curves also hints at variations in the initial conditions, such as the mass ratio of merging white dwarfs or the amount of accreted material. These uncertainties motivate ongoing studies with both observations and computer simulations. The physical environment inside a white dwarf before detonation is extreme in its own way. Densities approach 1,000,000 times that of water, and the material is a plasma of carbon and oxygen nuclei, immersed in a sea of degenerate electrons. The temperature required to ignite fusion under such conditions is lower than in normal stellar cores because degeneracy removes the stabilizing feedback between pressure and temperature. Once ignition begins, there is no way to quench it. The entire star burns within seconds, releasing energy equivalent to billions of nuclear bombs. The ejected material expands at thousands of kilometers per second, carrying with it the newly synthesized elements. The importance of Type Ia supernovae extends beyond their use as cosmic yardsticks. They contribute significantly to the chemical enrichment of galaxies. While core collapse supernovae supply large amounts of oxygen, magnesium, and other elements, Type Ia supernovae are the dominant source of iron. The iron found in planetary cores, in meteorites, and in the blood of living organisms ultimately originates from these explosions. Thus, the thermonuclear death of white dwarfs plays a central role in the evolution of galaxies and the formation of planets. Observations of Type Ia supernovae have advanced with the rise of wide-field surveys and rapid follow-up instruments. Early detection allows astronomers to trace the rise of the light curve from the very beginning, providing clues to the progenitor system. Some events show hints of interaction with surrounding material, while others appear remarkably clean. By comparing large samples, researchers refine models of how these explosions start and evolve. Future observations with space-based telescopes and gravitational wave detectors may provide direct evidence of white dwarf mergers, further clarifying the origins of these explosions. Astronomers seek to identify the kinds of stars that precede supernova explosions, because knowing the progenitors helps explain both the mechanisms and the environments in which the events occur. For core collapse supernova, The progenitors are massive stars, but they can take several distinct forms depending on their evolutionary history. The most common class of progenitors are red supergiants. These stars have initial masses between about 8 and 25 times that of the Sun. They expand enormously during their late stages, becoming cool, luminous and swollen giants with radii hundreds of times larger than the Sun. Their outer envelopes are dominated by hydrogen, and when they collapse, they typically produce what astronomers call Type II supernovae. The characteristic hydrogen lines in the spectra of these events confirm the presence of hydrogen-rich progenitors. Direct evidence for this link comes from archival images of galaxies where supernovae later appeared. In several cases, the exact red supergiant progenitor has been identified in pre-explosion photographs confirming decades of theoretical predictions. Some massive stars follow a different path, losing most of their hydrogen envelopes before collapse. If stellar winds are strong enough, or if interaction with a binary companion strips away the outer layers, the star may become a blue supergiant or even a Wolf-Rayet star. Wolf-Rayet stars are hot, compact and highly luminous objects that display strong emission lines of helium, nitrogen, carbon or oxygen in their spectra. These features indicate that nuclear process material from the core is exposed at the surface. Such stars are thought to be progenitors of hydrogen-poor explosions known as Type Ib and Type Ek supernovae. In these cases, the absence of hydrogen lines, and in some events even the absence of helium, matches the composition expected from stripped envelope stars. The diversity of progenitors also reflects the influence of metallicity, which is the abundance of elements heavier than helium. Stars in galaxies with higher metallicity tend to lose mass more effectively through winds, making them more likely to shed their envelopes and evolve into stripped stars. By contrast, in lower metallicity environments, weaker winds allow massive stars to retain more hydrogen, making red supergiant progenitors more common. Observations of supernovae across different galaxies support these trends, although many details remain uncertain. Binary systems introduce additional complexity. Many massive stars are in binaries, and interactions between companions often determine the final outcome. Mass transfer from one star to another can strip a star's hydrogen envelope, creating conditions for a stripped envelope supernova. Alternatively, mergers can produce unusually massive and luminous progenitors that explode in uncommon ways. Binary pathways also play a key role in Type Ia supernovae, as white dwarfs rely on mass transfer or mergers to trigger thermonuclear runaway. Thus, understanding progenitors requires not only considering the mass of a single star, but also its companions and environment. One famous example of an unexpected progenitor is the star that exploded as SN 1987 in the Large Magellanic Cloud. Instead of a red supergiant, the progenitor was a blue supergiant named Sanderleak -69202. This finding surprised astronomers because prevailing theory predicted red supergiants as the standard progenitors of Type II events. The case showed that multiple evolutionary pathways can lead to collapse, and that stellar models needed to account for mass loss mixing and binary interaction more carefully. SN 1987A remains a key example of how direct progenitor identification refines theoretical models. Beyond individual cases, surveys of nearby galaxies and long-term monitoring of massive stars are gradually building a statistical picture of progenitors. Catalogues of red supergiants and Wolf-Rayet stars provide potential candidates, and when one of them eventually explodes, astronomers can connect the dots between stellar type and explosion mechanism. The difficulty lies in the rarity of nearby supernovae. Only a handful occur per century in galaxies close enough for detailed pre-explosion images. Still, the accumulation of data is gradually confirming the theoretical framework. Identifying progenitors also helps link stellar life cycles to nucleosynthesis. Red supergiants contribute large amounts of hydrogen and helium to their surroundings when they explode, while stripped stars enrich the medium with heavier elements like carbon and oxygen. Wolf-Rayet progenitors in particular are associated with high mass loss rates, injecting chemically enriched material into their surroundings even before the final explosion. These differences shape the chemical fingerprints observed in supernova spectra and remnants. Another clue to progenitors comes from circumstellar material. Many massive stars lose mass through winds or eruptions shortly before collapse. When the supernova shock collides with this material, it produces narrow emission lines and enhanced brightness, creating a class of events known as interacting supernova. The presence of this circumstellar material indicates that the progenitor was unstable in its final years, shedding mass in ways not fully understood. Studying these interactions provides indirect evidence about the final stages of stellar evolution. In contrast, the progenitors of Type Ia supernovae remain elusive. Because the white dwarf itself is faint and compact, it is rarely detectable before explosion. Attempts to identify surviving companions after the explosion have had mixed results. Some remnants show no obvious donor star favoring double degenerate mergers. Others show hints of possible companions suggesting single degenerate channels. The uncertainty highlights how progenitor studies are essential for resolving the origins of these important events. Progenitor identification is more than a matter of classification. It provides crucial boundary conditions for models of stellar evolution and explosion. Without knowing the initial state of the star, it is difficult to test theories of how explosions proceed. By pinning down the properties of progenitors, astronomers can constrain the processes of mass loss, mixing rotation, and binary interaction that govern stellar evolution. Each identified progenitor adds a piece to this puzzle. This study of progenitors demonstrates the continuity between a star's quiet life and its final outburst. Red supergiants, blue supergiants, and Wolf-Rayet stars are observed in nearby galaxies shining in relative stability. Yet within thousands to millions of years, an instant in cosmic terms, they will end in collapse and explosion. White dwarfs linger for billions of years before suddenly igniting and unbinding. Progenitors therefore connect ordinary stellar observations to rare but transformative supernovae. By tracking their properties and lifetimes, astronomers prepare for the moment when one of these stars will light up the sky with a final display. Binary star systems play an essential role in shaping many of the pathways that lead to supernova explosions. While single stars can reach instability through their own evolution, the majority of massive stars exist in pairs or multiples, and their mutual interactions change the course of their lives in significant ways. When two stars orbit closely, mass transfer from one to the other becomes possible. The star that evolves more quickly may swell as it becomes a giant, and overflow its gravitational boundary known as the Roche lobe. Gas then streams onto its companion, altering the mass balance of the system. This process can strip the donor star of its outer layers, leaving a hydrogen-poor core. Such stripping explains how certain progenitors evolve into Wolf-Rayet stars, which later produce type Ib, or type EC supernovae with little or no hydrogen visible in their spectra. The star receiving mass may also be altered. Accretion increases its mass, sometimes pushing it above the threshold needed to undergo core collapse, sooner than it would have otherwise. In this way, binary mass transfer does not simply affect the donor, but reshapes the future of both stars. Some systems even undergo a common envelope phase in which one star engulfs the other inside its swollen outer atmosphere. Friction within the common envelope shrinks the orbit, bringing the stars close together, and leading either to a merger or to the ejection of the envelope. In both outcomes, the subsequent evolution is very different from what would occur in isolation. For white dwarfs, binary interactions are even more critical. A single white dwarf cannot explode as a Type Ia supernova without gaining mass from a companion. In the single degenerate channel, a white dwarf accretes matter from a red giant or main sequence star. This accretion can proceed through steady transfer of gas or through unstable bursts. When the accumulated mass drives the white dwarf near the Chandrasekhar limit runaway, thermonuclear fusion ignites. In the double degenerate channel, two white dwarfs spiral inward due to gravitational wave radiation. Over millions of years, their orbit shrinks until they merge. The violent collision either triggers immediate fusion or builds a super Chandrasekhar object that ignites shortly after. Both routes rely on binary evolution, showing how intimately linked these explosions are with companionship between stars. Observational evidence supports the importance of binaries. Many supernovae display features that point to interaction with surrounding material. Narrow spectral lines or unusual light curve shapes suggest that dense circumstellar gas was present before the explosion likely ejected during mass transfer. In some Type Ia events, excess ultraviolet radiation has been interpreted as the result of collision between supernova ejecta and a companion star, though such signals are rare. Statistical studies of stellar populations further confirm that the rate of certain supernova types cannot be explained without a high frequency of binary interaction. Mergers between stars also open pathways to unusual explosions. When two massive stars merge, the resulting single star may be more massive and more luminous than either original member. Such merger products can evolve differently, retaining large hydrogen envelopes or rotating rapidly. This may set the stage for rare kinds of supernovae such as those linked to long gamma-ray bursts. Although rare, these events highlight the extreme outcomes possible when binary interactions reshape stellar evolution. The role of metallicity appears again in the context of binaries. In environments with high metallicity, strong stellar winds remove mass efficiently, often preventing close interaction before collapse. In lower metallicity settings, weaker winds allow binaries to interact more directly, making mass transfer and mergers more common. This difference may explain why certain kinds of stripped envelope supernovae or gamma-ray burst-associated supernovae are more prevalent in low metallicity galaxies. One challenge in supernova science is reconstructing the exact binary history of a progenitor system after the explosion. Once a star has exploded, only indirect evidence remains. In some cases, astronomers have searched for surviving companion stars near supernova remnants. For example, the remnant of SN 1572, also known as Tycho's supernova, has been examined for such a companion. The results are debated, but possible candidates have been suggested. Similar searches in other remnants aim to test the single degenerate scenario for Type Ia supernovae. The absence of obvious companions in many cases pushes researchers to consider double degenerate models more seriously. The study of binaries extends beyond direct progenitors to the larger population of stars. Surveys show that a majority of massive stars are in binaries close enough to interact during their lifetimes. This statistic alone implies that binary effects cannot be ignored when modeling the origins of supernovae. Theoretical models of binary evolution incorporate mass transfer, common envelope phases, orbital decay, and mergers, all of which feed into predictions of supernova rates and types. These models must match the observed distribution of supernovae in galaxies, providing a stringent test of stellar evolution theory. Accretion physics also plays a significant role in determining outcomes. The rate at which matter flows from a companion onto a white dwarf affects whether fusion proceeds stably or explosively. If the accretion is too slow, the material can burn steadily without runaway. If too rapid, instabilities may trigger nova outbursts that blow material away before the white dwarf can gain enough mass. Only in a narrow range of conditions does the mass accumulate efficiently to bring the white dwarf to detonation. Such sensitivity underscores how precise the balance must be for a Type Ia supernova to occur. In recent years, computer simulations of binary interactions have improved, but uncertainties remain. Hydrodynamic codes explore how matter transfers between stars, how envelopes are ejected, and how mergers proceed. These simulations require significant computational resources, as the flows involve turbulence, shocks, and radiation. Nevertheless, progress is being made, and comparisons with observations of binary star populations help calibrate the models. Gravitational wave astronomy promises to add new insights, as detectors improve. Merging white dwarfs and possibly even massive star binaries may be observed through their gravitational signals. Detecting such systems before they explode would provide direct evidence of binary channels leading to supernovae. Combined with electromagnetic surveys, this multi-messenger approach could reveal the full history of a progenitor system. The prominence of binaries in supernova origins shows that the life of a star is often not an isolated journey. Companion stars influence mass rotation and chemical makeup, all of which determine the path to explosion. The transfer of matter, the tightening of orbits, and the eventual merging of stellar cores create a diversity of outcomes that enrich galaxies with elements and light. By tracing these interactions, astronomers come closer to understanding why stars die in so many different ways, and why supernovae themselves are such a varied family of cosmic events. The collapse of a massive star into a supernova involves a chain of physical processes that operate on extreme scales of density, temperature, and energy. At the center is the transformation of the stellar core into matter dominated by neutrons, while the surrounding layers respond to the sudden loss of support and the surge of neutrino emission. The physics of this collapse and explosion has been a central focus of astrophysics for decades, with advances in both observation and theory gradually clarifying the steps. When nuclear fusion in the core produces ion energy, generation ceases. Gravity then overwhelms the pressure that has balanced it for millions of years. The core contracts rapidly, and as it does, the electrons are forced into protons, producing neutrons and neutrinos. The density rises to nuclear levels around 10 to the power of 14 grams per cubic centimeter. At this density, the strong nuclear force resists further compression, and the inner core halts suddenly. The outer core, still collapsing, slams into this halted region, generating a shock wave that begins to move outward. This initial shock is powerful, but it quickly loses energy by breaking apart iron nuclei into free particles and by radiating copious neutrinos. The stalled shock is one of the great puzzles of core collapse supernova physics. If it remains stalled, the star would collapse inward without an explosion, producing only a compact remnant. To explain the observed explosions, researchers developed the idea of neutrino heating. Although neutrinos interact only weakly with matter, the density just outside the proto-neutron star is high enough that a small fraction of them deposit energy. Over time, this heating builds pressure behind the shock, aiding its revival. Convection and turbulence in the hot material amplify the effect, stirring the layers and increasing the efficiency of energy transfer. Three-dimensional simulations show that these chaotic motions are essential to push the shock outward. In addition to neutrinos, other factors may influence the explosion. Rapid rotation of the core can create strong centrifugal forces and may lead to the formation of jets that help channel energy outward. Magnetic fields wound up by the collapse, and rotation may also contribute. In highly magnetized and rapidly rotating cores, the magnetic energy can dominate, producing what are known as magneto-rotational supernovae. These are candidates for powering hyper-energetic explosions, and possibly the long-duration gamma-ray bursts observed in some galaxies. However, such conditions appear rare, and most core collapse events are thought to be driven primarily by neutrino heating. The success or failure of the explosion depends sensitively on the mass of the core and the envelope. Stars on the lower end of the massive star range may produce relatively weak explosions, ejecting only part of their material. Some may collapse into neutron stars with small kicks that propel them through space. More massive stars may fail to explode successfully with a shock never fully revived. In these cases, the outer layers fall back onto the core and the star collapses directly into a black hole. Such failed supernovae are difficult to observe, but surveys have identified candidates where a massive star seemed to vanish without a bright explosion. These quiet endings represent an important boundary in the physics of collapse. Evidence supporting neutrino-driven explosions comes from both theory and observation. The detection of neutrinos from SN 1987A confirmed that enormous numbers of neutrinos are emitted during core collapse. Although only a small number of events were recorded, they match predictions of energy and timing. More recently, simulations incorporating neutrino transport and turbulence have succeeded in producing explosions under realistic conditions, though the exact thresholds remain sensitive to assumptions about nuclear physics. The nuclear physics itself is a vital component of the collapse. The behavior of matter at densities beyond atomic nuclei is uncertain. This so-called nuclear equation of state, which relates pressure, density, and temperature, influences how the core responds during collapse. A stiffer equation of state provides more resistance, aiding the bounce and the shock, while a softer one may favor black hole formation. Laboratory experiments in nuclear physics help constrain these properties, but only supernova cores reach the required conditions in nature. Thus, supernova observations feed back into fundamental physics, offering clues about the state of matter under extreme compression. Another aspect of core collapse physics involves asymmetry. Observations of supernova remnants and neutron star velocities show that explosions are rarely perfectly spherical. Many neutron stars move through space at hundreds of kilometers per second, propelled by asymmetric ejection of matter. Simulations reveal that convection and turbulence naturally break spherical symmetry, creating lopsided explosions. These asymmetries also influence the distribution of heavy elements in the ejector, leaving imprints on the chemical structure of the expanding remnant. The role of instabilities further shapes the outcome. Phenomena such as the standing accretion shock instability, often abbreviated SARSI in research literature, cause the shock front to wobble and oscillate. These oscillations help redistribute energy and promote explosion, while also imparting directional kicks to the forming neutron star. The presence of such instabilities in simulations supports the idea that chaotic processes are central to turning a stalled shock into a successful explosion. The timescales involved in core collapse physics highlight the extremes of astrophysics. The collapse itself occurs in less than a second. The shock stalls within milliseconds and may take hundreds of milliseconds to revive. Neutrino emission continues for tens of seconds as the proto-neutron star cools and contracts. The expanding shock reaches the surface of the star within minutes to hours, producing the initial flash of light. The full light curve then unfolds over weeks to months as radioactive decay powers the visible emission. This sequence shows how events unfolding in fractions of a second shape the light we observe for months. Observations across the spectrum support and refine these models. X-ray and radio observations of supernova remnants reveal the distribution of ejected material, showing evidence of asymmetry and clumping. Optical spectra provide velocities and compositions of different layers. Polarization measurements confirm that the explosions are not spherical. Each piece of data adds to the picture of how the core collapse mechanism operates in practice. The link between the collapse of a massive core and the birth of compact objects makes this process a cornerstone of astrophysics. Neutron stars, magnetars, and black holes are all products of these physical steps. The details of how the shock is revived, how asymmetries arise, and how much mass falls back determine which remnant is left behind. Supernovae are therefore not only luminous explosions, but also the origin points of the most extreme stellar objects in the universe. The physics of core collapse represents a bridge between many disciplines. It connects stellar evolution nuclear physics, neutrino physics, hydrodynamics, and magnetism. Progress in understanding it comes from the combination of simulations, laboratory experiments, and astronomical observations. Each observed supernova, each remnant, and each detection of neutrinos provides a test of the models. Step by step, the complex chain of collapsed neutrino heating, turbulence, and shock revival becomes clearer, though open questions remain about the role of rotation, magnetic fields, and the precise equation of state. In contrast to core collapse events, thermonuclear supernovae originate in white dwarfs that undergo runaway fusion. The physics of these explosions differs fundamentally because they are not triggered by gravitational collapse, but by nuclear ignition in degenerate matter. A white dwarf formed from the remnant of a low or intermediate mass star is supported against gravity by electron degeneracy pressure. This pressure depends only on density, not on temperature, which means that when fusion begins, the usual regulating feedback of thermal expansion does not occur. Instead, the reactions accelerate uncontrollably, consuming the star in seconds. The process starts when a white dwarf gains mass through accretion from a companion or through merger with another white dwarf. As its mass approaches the Chandrasekhar limit, the central density rises to several times 10 to the power of 9 grams per cubic centimeter. At these densities, the temperature required for carbon fusion is reached, and fusion ignites in a small region. Because the matter is degenerate, the temperature rise does not cause expansion and cooling. The fusion front spreads outward initially as a subsonic flame known as a deflagration. In some models, this flame later transitions into a detonation, a supersonic shock-driven front that sweeps through the star. The deflagration to detonation transition remains an area of intense study, as it determines the structure of the ejector and the amount of radioactive material produced. The key product of the explosion is nickel-56, a radioactive isotope. During the burning, large fractions of carbon and oxygen are fused into nickel-56, which later decays to cobalt-56 and then to stable iron-56. Each step of the decay chain releases gamma rays and positrons, which deposit energy into the expanding debris and power the observed light curve. The amount of nickel-56 synthesized directly controls the brightness of the event. This is why Type Ia supernovae are so luminous, and why their peak brightness is relatively uniform. Simulations show that the exact outcome depends on initial conditions such as the ignition point, the density at ignition, and whether a detonation occurs. In pure deflagration models, the burning is incomplete, leaving behind unburned carbon and oxygen. In detonation models, the burning is more complete, producing more nickel-56. In reality, observations suggest that many explosions involve both processes. The mixture explains why spectra show both intermediate mass elements like silicon and sulfur, as well as and group elements. The presence of silicon absorption lines near maximum light is one of the defining features used to classify Type Ia events. Mergers of two white dwarfs represent another path to detonation. In such systems, gravitational radiation causes the orbit to shrink until the stars collide. The less massive star is disrupted and accreted onto the more massive one, raising the density and temperature until ignition occurs. Alternatively, the merger may lead to the formation of a super Chandrasekhar mass white dwarf that ignites after a delay. The diversity of possible outcomes may account for variations observed in Type Ia supernova light curves. Some are slightly brighter, suggesting more nickel-56, while others are dimmer perhaps from incomplete burning or lower total mass. Despite differences, the relative uniformity of Type Ia explosions makes them invaluable in cosmology. Their predictable peak brightness allows astronomers to use them as standardizable candles for measuring distances across the universe. Corrections based on the width of the light curve reduce the scatter in brightness, enabling precise distance estimates. This property led to the discovery in the late 1990s that distant supernovae appeared dimmer than expected, indicating that the expansion of the universe is accelerating. The finding introduced the concept of dark energy, a mysterious component of the cosmos that drives accelerated expansion. Beyond cosmology, thermonuclear supernovae are also central to galactic chemical evolution. They are the primary producers of iron and contribute significantly to other iron group elements. Core collapse supernovae enrich galaxies with oxygen, neon, and magnesium, while Type Ia explosions provide the iron that accumulates in planetary interiors and in stars like the Sun. The relative timing of these contributions is important. Core collapse events occur promptly after star formation within tens of millions of years, while Type Ia supernovae arise on longer timescales ranging from hundreds of millions to billions of years. This delay explains why galaxies show different chemical abundance patterns depending on their star formation histories. Observations across the electromagnetic spectrum refine understanding of these explosions. Optical surveys reveal light curves and spectra, while X-ray studies of supernova remnants show the distribution of iron and other heavy elements. Ultraviolet observations probe early phases, sometimes revealing interaction with circumstellar material. Infrared data help track dust formation in the ejecta. Each wavelength adds information about how the explosion proceeds and what it leaves behind. Despite progress, open questions remain. The relative contributions of single degenerate accretion and double degenerate mergers are debated. Direct detection of progenitor systems has been elusive, as white dwarfs and their companions are faint. Searches for surviving companions in remnants sometimes yield candidates, but the evidence is inconclusive. Future observations with gravitational wave detectors may identify merging white dwarfs before detonation, offering direct confirmation of one pathway. Similarly, improved time domain surveys that catch supernovae at the moment of explosion may reveal telltale signatures of companion interaction, such as excess early light. The physics of thermonuclear supernovae links small-scale nuclear reactions with galaxy-scale evolution. Carbon and oxygen nuclei fuse into nickel in fractions of a second, yet the products enrich interstellar gas for billions of years. The explosions transform invisible compact remnants into events visible across the observable universe. This connection between quantum processes in dense matter and cosmological expansion makes Type Ia supernovae uniquely significant. Laboratory experiments cannot reproduce the densities and degeneracy of white dwarfs, so these explosions provide the only direct evidence of nuclear flames in such conditions. Computer simulations attempt to model the turbulent deflagration front, the possible detonation and the resulting structure of the ejecta. Comparing these models with observed spectra and light curves guides refinements, but the complexity of turbulence and nuclear burning remains a challenge. Even so, the broad outline is clear: when a white dwarf gains too much mass fusion, ignites under degenerate conditions, spreads uncontrollably and tears the star apart. The outcome leaves no remnant, only an expanding cloud of hot gas rich in iron and nickel. As the ejecta expand, they collide with interstellar gas, forming remnants that can be studied for centuries. These remnants, glowing in X-ray and optical emission, provide further information about the yields of the explosion and the structure of the debris. By comparing remnants with models, astronomers continue to refine their understanding of how thermonuclear supernovae proceed and what they contribute to the cosmos. The first visible sign of a supernova explosion comes when the shock wave generated deep within the star reaches the stellar surface. This moment, known as shock breakout, represents the transition from a hidden process inside the star to an observable event that radiates across space. The shock front, carrying energy deposited by collapse or thermonuclear ignition, accelerates outward through the stellar envelope. As it propagates, it heats and compresses the surrounding layers, but the dense outer layers of the star trap photons, preventing light from escaping. Only when the shock reaches the very edge of the star does radiation burst free in a sudden and intense flash. The characteristics of shock breakout depend strongly on the type and size of the progenitor. For a red supergiant with its vast extended atmosphere, the breakout lasts longer and is cooler, radiating primarily in the ultraviolet and optical bands. For a more compact blue supergiant or a stripped Wolf-Rayet star, the breakout is hotter and briefer, producing a pulse dominated by X-rays. In every case, the duration is short compared to the months-long light curve that follows. Shock breakout may last only minutes to hours, yet it carries crucial information about the size and structure of the progenitor star. Capturing this fleeting event requires wide-field monitoring and rapid response, and only in recent years have astronomers been able to detect it directly in several cases. Following shock breakout, the expanding debris becomes the main source of observable light. The outer layers, heated to tens of thousands of degrees, radiate energy as they expand and cool. In hydrogen-rich Type II supernovae, the cooling outer envelope produces a plateau of nearly constant brightness that can last for more than 100 days. This plateau arises because hydrogen recombination releases energy steadily as the ejecta expand. In contrast, hydrogen-poor events such as Type Ia Typeus and Type Ia supernovae show a more rapid rise to peak brightness followed by a decline. The shape of these light curves reflects the composition, mass, and opacity of the ejecta. Spectroscopic observations provide further detail. As the ejecta expand, absorption and emission lines from different elements appear in the spectrum. In Type II events, prominent hydrogen lines confirm the presence of extended hydrogen envelopes. In Type Ib supernovae, helium lines are visible, while in Type Ike they are absent, indicating more complete stripping of the outer layers. Type Ia supernovae display silicon lines near maximum light, followed by iron group lines as the ejecta cool. By analyzing these spectral features, astronomers identify both the type of supernova and the physical conditions within the expanding gas. Shock breakout and the early rise of the light curve also serve as tests of models of explosion mechanisms. The timing of the breakout depends on how quickly the shock moves through the star and how much energy it carries. A weak or failed explosion may produce little or no observable breakout, while a strong shock yields a bright flash. Observations of early light curves can therefore constrain whether neutrino heating rotation or magnetic fields were sufficient to revive the stalled shock in core collapse events. For thermonuclear explosions, the presence of excess early light can indicate interaction with a companion star as the ejecta collide with it and produce additional emission. Such signatures have been sought in Type Ia events to distinguish between single degenerate and double degenerate progenitor scenarios. In addition to optical and ultraviolet signals, neutrinos provide the earliest detectable sign of core collapse. Because they escape directly from the dense core, they arrive hours before the first photons are visible. The detection of neutrinos from SN 1987A provided direct confirmation of this prediction. Modern neutrino detectors are poised to capture thousands of neutrinos from the next nearby supernova, offering a detailed view of the collapse process. These neutrino signals can reveal the timescale of core bounce, the energy of emission, and the cooling history of the forming neutron star. They represent a direct probe of the physics deep inside the star, complementing the more delayed electromagnetic display. Gravitational waves are another potential early signal. The collapse of the core, the turbulent revival of the shock and asymmetries in the explosion can all generate gravitational radiation. Although no gravitational waves from a supernova have yet been detected, future improvements in sensitivity may allow such detections. Like neutrinos, gravitational waves carry information from the core that cannot be obtained by light alone. Together, neutrinos, gravitational waves, and electromagnetic radiation form a multi-messenger picture of supernovae connecting processes at the heart of the explosion with the observable features in the sky. The interplay between shock breakout, early light, and later emission emphasizes the importance of continuous monitoring. Wide-field surveys now scan large areas of the sky every night, capturing transients as they appear. When a new supernova is discovered, follow-up observations across many wavelengths track its evolution from breakout to peak and decline. The combination of early detection and multi-wavelength coverage allows astronomers to reconstruct the conditions of the progenitor star and the dynamics of the explosion. Examples of observed shock breakout illustrate these principles. In 2008, a supernova in a distant galaxy was caught by chance during its breakout in X-rays lasting only a few minutes. The data provided direct evidence for the size and structure of the progenitor. More recently, time-domain surveys have identified rising light curves within hours of explosion, enabling detailed modeling of progenitors. Each detection adds to the growing dataset that constrains stellar evolution and explosion models. As the ejecta expand, the supernova enters a phase where radioactive decay becomes the dominant power source. The decay chain of nickel-56 to cobalt-56 and finally to iron-56 releases gamma rays that heat the gas. At early times, the gamma rays are trapped and converted into optical light, producing the bright peak of the light curve. As the ejecta-thin gamma rays begin to escape and the light curve declines, the rate of decline provides a measure of the nickel mass synthesized in the explosion, linking observations directly to nuclear processes in the star. The first signs of a supernova, from neutrino burst to shock breakout and early light, thus connect the hidden physics of collapse or runaway fusion to the luminous display that follows. Observations of these stages are challenging but increasingly successful, thanks to advances in detectors and surveys. By capturing the moment when light first escapes, astronomers gain a direct window into the conditions of the progenitor star and the mechanics of the explosion itself. Once the initial flash of a supernova fades, the long-lasting light curve and the evolving spectrum provide the main clues to the physics of the explosion. A light curve is a record of brightness over time, and its shape is determined by how energy is deposited and radiated in the expanding debris. The peak luminosity, the rate of decline, and the presence of plateaus or secondary maxima vary between types of supernovae, offering a way to classify and understand them. In Type 2 supernovae, where the progenitor retains a large hydrogen envelope, the light curve often shows a plateau lasting about 100 days. During this time, the hydrogen envelope cools and recombines, releasing energy steadily and producing a relatively flat brightness profile. These Type 2p supernovae are among the most common and provide direct evidence of red supergiant progenitors. In some cases, instead of a plateau, the decline is more linear, producing what astronomers call Type 2L events, thought to arise from stars that lost more of their hydrogen before collapse. In hydrogen-poor explosions such as Type Ib and Type Ic, the light curve behaves differently. Without a massive envelope, the ejecta expand and cool more quickly, and the brightness peaks earlier and declines more smoothly. These explosions are powered primarily by radioactive decay of nickel-56, whose presence is revealed by both the light curve and the spectra. Type Ia supernovae. The thermonuclear explosions of white dwarfs display remarkably uniform light curves. They rise to a sharp peak within about 20 days and decline at a rate that correlates with peak brightness. This relationship, known as the Phillips relation, allows astronomers to standardize type Ia events as cosmic distance indicators. By correcting for the width of the light curve, they can measure distances with precision across cosmological scales. Spectra taken at different times reveal the chemical composition and velocity of the ejecta. At early times, broad absorption features dominate, caused by rapidly expanding material absorbing light at specific wavelengths. The width of these lines corresponds to velocities of thousands of kilometers per second. In Type II, spectra hydrogen lines are clear, often showing a P Cygni profile that indicates both emission from the expanding shell and absorption from material moving toward the observer. As the supernova ages, deeper layers become visible, and the spectra reveal elements such as oxygen, calcium, and iron. In Type Ib, supernovae helium lines stand out, while in Type Isc these are absent, replaced by signatures of heavier elements. In Type Ia events, strong silicon absorption at maximum light provides the defining characteristic, later giving way to lines from iron group elements as the ejecta cool. Polarization measurements add further insight. If the ejecta are perfectly spherical, polarization cancels out and little signal is seen. But many supernovae show measurable polarization, indicating asymmetry in the explosion. These asymmetries support the picture of turbulence and instabilities, driving core collapse explosions, as well as the possibility of clumpy burning fronts in thermonuclear events. Observations of polarization over time track how the geometry evolves as different layers of the ejecta become visible. Light curves also reveal unusual subclasses. Some supernovae are far brighter than typical, reaching luminosities more than 10 times higher. These superluminous supernovae are rare and may be powered by additional energy sources such as the spin-down of a rapidly rotating magnetar or interaction with dense circumstellar material. Others fade unusually quickly or show peculiar spectra, challenging simple classification. Each new example expands the diversity of known outcomes and tests models of stellar explosions. Radio and X-ray observations extend the picture beyond optical light. When supernova ejecta collide with circumstellar material shed by the progenitor, before explosion shocks accelerate particles and produce synchrotron radiation visible in radio wavelengths. X-rays trace hot plasma in the shocked gas. These signals reveal the mass loss history of the progenitor, providing indirect evidence of how the star evolved in its final stages. Some interacting supernovae, especially of Type II, show strong and prolonged emission from such interactions, pointing to massive pre-explosion outbursts. Infrared observations detect dust forming in the cooling ejecta. As temperatures drop, atoms and molecules condense into solid grains, which absorb optical light and re-radiate it in the infrared. Supernovae are therefore important contributors to cosmic dust, which later plays roles in star and planet formation. Infrared spectra also reveal molecular lines such as those of carbon monoxide, offering additional probes of ejecta chemistry. The transition from the photospheric phase, where the ejecta are opaque, to the nebula phase, where they are transparent marks, a key change in the observable properties. Months after the explosion, the spectra become dominated by emission lines from forbidden transitions of oxygen, calcium, and iron. These lines provide direct measurements of the abundances of different elements and the structure of the ejecta. Nebula spectra are particularly valuable for comparing with nucleosynthesis models because they reflect the yields of the explosion without the complications of radiative transfer in optically thick gas. The combination of light curves, spectra, and polarization allows astronomers to reconstruct both the physics of the explosion and the nature of the progenitor. For example, a plateau light curve combined with hydrogen-rich spectra points to a red supergiant progenitor with an intact envelope. A fast-declining light curve without hydrogen, but with helium lines, points to a stripped star, while a silicon absorption feature at peak brightness confirms a Type Ia event. In this way, observations serve as fingerprints of the underlying processes. The precision of these diagnostics depends on the quality of monitoring. Modern surveys using wide-field telescopes scan the sky regularly, discovering thousands of supernovae each year. These discoveries are followed by spectroscopic classification and multi-wavelength campaigns that track the evolution over time. The resulting datasets allow statistical studies of supernova populations, revealing correlations between progenitor environments, explosion properties, and host galaxies. Such studies show, for example, that hydrogen-rich core collapse events are more common in star-forming galaxies, while Type I supernovae occur in both young and old stellar populations. The study of light curves and spectra illustrates the value of detailed step-by-step observation. Each stage of the explosion reveals a different layer of information. The breakout flash signals the progenitor's size, the early rise reflects the distribution of nickel and the opacity of the ejecta. The peak brightness measures radioactive yield. The decline shows transparency to gamma rays, and the nebula spectra display the elemental composition. Together, these observations trace the complete physical story of the explosion from initial energy release to final dispersal of elements into space. While light curves and spectra provide rich information about the expanding ejecta, other messengers carry signals directly from the heart of the explosion. Chief among these are neutrinos and gravitational waves. Neutrinos are nearly massless particles that interact so weakly with matter that they can escape from regions opaque to light. In a core collapse supernova, the newly forming protoneutron star radiates an immense burst of neutrinos, carrying away the majority of the gravitational energy released during collapse. The total energy emitted as neutrinos exceeds the entire radiant output of all the stars in the observable universe during those few seconds. Yet because neutrinos interact so little, only a tiny fraction reach detectors on Earth. The detection of neutrinos from SN 1987A provided a landmark confirmation of theoretical predictions. Underground detectors in Japan, the United States, and Russia recorded a few dozen neutrino events within a time span of about 12 seconds. These detections, sparse as they were, matched the expectations of a core collapse, producing a protoneutron star that cools by neutrino emission. The arrival of neutrinos hours before visible light reached Earth also confirmed that they escape immediately from the dense core, while photons are delayed until the shock reaches the surface. Modern neutrino observatories such as Super Kamiokande in Japan and IceCube in Antarctica are poised to detect thousands of neutrinos from the next nearby supernova, providing an unprecedented view of the dynamics of collapse and cooling. The neutrino signal is expected to have several distinct phases. At the moment of core bounce, a sharp spike of electron neutrinos is released as protons and electrons combine into neutrons. This is followed by a more prolonged emission, as the protoneutron star radiates neutrinos of all flavors during its cooling phase. The luminosity gradually declines over tens of seconds. The spectrum of neutrino energies reflects the conditions deep in the star, offering a direct probe of nuclear matter at extreme density. By comparing the timing and distribution of neutrino detections, physicists can test models of neutrino oscillations, in which neutrinos change flavor as they propagate. A nearby supernova would therefore provide not only astrophysical insight, but also fundamental information about particle physics. gravitational waves, ripples in the fabric of space-time predicted by general relativity, represent another potential signal. The collapse of a star's core is not perfectly symmetric, especially when turbulence, convection, and instabilities dominate. These asymmetries produce time-varying quadrupole moments that generate gravitational radiation. Although the amplitude is small, detectors such as LIGO and Virgo are sensitive to strains of order 1 part in 10 to the 21. A nearby supernova within our galaxy could produce a detectable burst of gravitational waves lasting a few hundred milliseconds. The precise shape of the waveform would reveal details of the collapse, the bounce, and the growth of instabilities. Simulations suggest that features such as the standing accretion shock instability, with its characteristic sloshing motions, could imprint distinct patterns in the gravitational wave signal. Rapid rotation and magnetic fields could add further signatures, especially if jets form. Detecting such signals would allow astrophysicists to reconstruct the dynamics of the core in real time. No gravitational waves from a supernova have yet been observed, but with the ongoing operation of advanced detectors and planned upgrades, the likelihood of capturing one in the next galactic event is high. The combination of neutrinos and gravitational waves with electromagnetic light creates what is known as multi-messenger astronomy. Each messenger probes a different region of the explosion. Neutrinos emerge directly from the dense core. Gravitational waves trace bulk motions of matter, and asymmetries and photons reveal the slower evolution of the ejector. Together they provide a complete picture of how a massive star dies. The arrival times of the signals also offer cross-checks. Neutrinos arrive first, gravitational waves nearly simultaneously, and light hours later when the shock reaches the surface. Detecting all three from the same event would provide the most detailed record ever of stellar death. Particle detectors and gravitational wave observatories are part of an international network designed to alert astronomers to a nearby supernova in real time. The Supernova Early Warning System, or SNEWS, coordinates neutrino detectors around the world. When several detectors register a burst, an alert is sent to the astronomical community, allowing telescopes to begin monitoring before light emerges. This capability means that the next galactic supernova will be observed from its very beginning across the full spectrum and through multiple messengers. Such observations will test models of core collapse more rigorously than ever before. Beyond core collapse, supernovae, type Ia explosions may also produce distinct signals. Although they are not expected to emit large numbers of neutrinos, mergers of white dwarfs should produce gravitational waves during the inspiral phase. These waves are at lower frequencies, best detected by planned space-based observatories such as LISA. Observing such signals would confirm the double degenerate pathway to type Ia explosions, and allow measurement of the properties of the merging stars. In this way, gravitational wave astronomy connects to both core collapse and thermonuclear supernovae. Cosmic rays provide yet another form of energetic particle linked to supernovae. The shock waves generated as supernova ejecta sweep through interstellar space accelerate protons and electrons to relativistic speeds. These particles fill the galaxy, contributing to the high-energy radiation that constantly bombards Earth. While not direct messengers from the explosion itself, cosmic rays are a long-term product of supernova activity and further demonstrate the diverse ways in which these events shape their environments. The role of neutrinos and gravitational waves extends beyond confirming explosion mechanisms. They also probe physics under conditions inaccessible on Earth. Neutrino interactions reveal properties of nuclear matter, neutrino masses and oscillations. Gravitational waveforms test general relativity in the strong field regime. Supernovae therefore function as natural laboratories for both astrophysics and fundamental physics. Each nearby event becomes an experiment conducted by nature, with detectors on Earth serving as the instruments. The expectation of capturing a galactic supernova in the era of multi-messenger astronomy drives preparations across the scientific community. Neutrino detectors refine their triggers, gravitational wave observatories upgrade their sensitivity, and telescopes coordinate rapid response. The rarity of such events, perhaps only a few per century in the Milky Way, makes preparation essential. When the next one occurs, the combined data will illuminate not only the death of a star, but also the workings of the fundamental laws of physics. The faint neutrino detections of 1987 mark the beginning of this field. Future observations promise vastly more detail, with thousands of neutrinos' potential gravitational waves and full electromagnetic coverage. Each messenger adds a piece to the puzzle, and together they will finally reveal the intricate physics that governs the violent yet ordered end of massive stars. A defining consequence of supernova explosions is nucleosynthesis, the creation of new atomic nuclei. Stars throughout their lifetimes forge elements through fusion, but their range is limited. In normal stellar interiors, fusion proceeds only up to iron, because beyond iron fusion consumes energy rather than releasing it. The explosive conditions of supernovae, however, open additional pathways that form many of the heavier elements of the periodic table. These processes, operating in fractions of a second within collapsing cores and expanding ejecta, are responsible for the cosmic abundance of elements essential to planets and life. In core collapse supernova, several nucleosynthesis mechanisms operate. The shock wave passing through the silicon-rich layers of the progenitor compresses and heats matter to billions of degrees. Under these conditions, nuclei undergo explosive silicon burning, producing iron group elements, such as nickel, cobalt, and iron. At the same time, lighter nuclei are fused into intermediate mass elements like calcium, sulfur, and argon. The resulting distribution of elements depends on the peak temperatures and densities reached in each layer. Because different shells of the progenitor star are heated to different extents, the explosion produces a layered pattern of new elements that later disperse into space. Another important process in core collapse supernovae is the rapid neutron capture process, or R process. When the collapsing core generates a flood of neutrons, some regions become so neutron-rich that nuclei capture neutrons faster than they can decay. This rapid sequence drives nucleosynthesis to very heavy elements beyond iron, including gold, platinum, and uranium. The R process has long been suspected as the origin of these elements, and core collapse supernovae were once considered the primary site. Recent evidence suggests that neutron star mergers also contribute, but supernovae remain a viable environment for at least part of the R process. The exact conditions that enable it, such as the neutron density and the role of neutrino-driven winds, continue to be investigated. Thermonuclear supernovae, by contrast, produce elements mainly in the iron group. When a white dwarf undergoes runaway fusion, carbon and oxygen are rapidly fused into nickel-56 and related isotopes. As the explosion expands, radioactive decay of nickel-56 to cobalt-56 and then to iron-56 releases energy that powers the light curve. These isotopes also account for the large iron contribution of type-wire supernovae to galactic chemical evolution. While core collapse events provide more oxygen, magnesium, and silicon, thermonuclear explosions dominate the iron budget of galaxies. This distinction explains why abundance ratios of oxygen to iron differ between galaxies with rapid star formation and those with slower histories. Supernova nucleosynthesis is not only theoretical, but confirmed through observations. Spectra of supernovae show lines from newly formed elements at different stages. Early spectra may be dominated by lighter elements like oxygen and magnesium, while later nebula spectra reveal strong emission from iron and nickel. The detection of cobalt lines during decline directly traces the decay chain from nickel to cobalt to iron. In supernova remnants, X-ray spectroscopy reveals the distribution of elements such as silicon, sulfur, calcium, and iron. Maps of remnants show clumps and asymmetries indicating that the nucleosynthesis was not uniform, but shaped by instabilities during the explosion. One of the most direct pieces of evidence comes from the detection of gamma rays emitted by radioactive decay. Observations of SN 1987A revealed gamma rays consistent with the decay of cobalt-56, confirming that large amounts of nickel-56 had been synthesized. In the Milky Way, gamma-ray telescopes detect emission from isotopes such as titanium-44 and aluminum-26, long-lived radioactive products of supernovae. These detections confirm ongoing nucleosynthesis in the galaxy and provide quantitative estimates of production rates. Dust formation is another outcome of nucleosynthesis in supernova. As the ejecta expand and cool, newly formed elements condense into solid grains. Observations in the infrared show emission from warm dust forming months to years after explosion. Supernovae are therefore important sources of interstellar dust, which later influences star formation and planet building. The large dust masses inferred in some young remnants suggest that these events may be especially important in the early universe, where other dust sources were scarce. The dispersal of elements from supernovae enriches the interstellar medium. Each explosion ejects several solar masses of material into its surroundings at high velocity. This material mixes with interstellar gas, altering its composition. Subsequent generations of stars form from enriched gas inheriting the heavy elements. This gradual enrichment over billions of years explains the increasing metallicity of stars in the galaxy. It also accounts for the presence of elements essential to rocky planets and biological systems. Without supernova nucleosynthesis, the universe would contain only hydrogen, helium, and traces of lithium. The periodic table as we know it is largely the product of these explosive processes. The study of supernova nucleosynthesis connects astrophysics to cosmochemistry. Analyses of meteorites reveal isotopic anomalies that trace back to specific nucleosynthesis processes. Grains of presolar material preserved within meteorites show compositions consistent with formation in supernova ejecta. These grains carry direct samples of nucleosynthesis across billions of years, linking laboratory measurements to stellar explosions. The isotopic ratios of oxygen, silicon, and other elements confirm models of explosive burning and provide constraints on conditions during the explosion. Theoretical models of nucleosynthesis require accurate nuclear reaction rates. Many of these rates involve unstable isotopes that are difficult to measure experimentally. Nuclear physics laboratories work to provide these rates, while supernova models incorporate them to predict yields. Comparison with observed abundances in stars and galaxies tests the accuracy of the models. For example, the relative abundances of elements in old stars of the galactic halo provide a record of the earliest nucleosynthesis events. These observations show patterns consistent with contributions from core collapse supernovae supporting their role in enriching the early universe. The significance of supernova nucleosynthesis extends to the very structure of the Earth and life itself. The iron in the core of the planet, the oxygen in its atmosphere, the calcium in bones, and the potassium in cells were all produced in stellar explosions. This scientific conclusion is based not on philosophical reflection, but on measured abundances, nuclear physics, and observed spectra. By tracing the origins of elements, scientists link the processes of distant stellar death to the material foundation of the solar system. The ongoing challenge is to refine the picture of which environments produce which elements. While core collapse supernovae clearly synthesize many intermediate and heavy elements, the relative contribution of R-process elements from supernovae versus neutron star mergers remains under debate. Improved models of neutrino-driven winds and multidimensional simulations of collapse may clarify whether conditions in supernovae suffice to produce the heaviest nuclei. Observations of kilonovae from neutron star mergers rich in R-process material show that multiple sites likely contribute. In this way, supernova nuclear synthesis is part of a broader cosmic cycle of element formation. Supernova explosions are therefore both destructive and creative. They end the lives of stars but seed galaxies with the building blocks of planets and organisms. The nuclear reactions that take place in their fleeting moments shape the long-term chemical evolution of the cosmos. Each element heavier than helium owes its existence to the extreme environments of stellar interiors and explosions, with supernovae serving as a central engine of transformation. After a supernova has expelled its outer layers, the stellar core undergoes a final transformation into a compact object. The nature of this remnant depends on the mass of the collapsing core, the dynamics of the explosion, and the amount of fallback material that returns after the blast. The two primary outcomes are neutron stars and black holes, though within these categories further diversity exists. These compact remnants are among the most extreme objects in the universe, and their study reveals not only the aftermath of supernovae, but also the physics of matter under extraordinary conditions. If the collapsing core has a mass below about 3 times that of the Sun, neutron degeneracy pressure halts further collapse, leaving behind a neutron star. A neutron star typically has a mass between about 1 and 2 solar masses, but is compressed into a sphere only about 20 kilometers in diameter. The density of such an object is comparable to that of atomic nuclei, meaning that a teaspoon of neutron star matter would weigh billions of tons. Neutron stars rotate rapidly, conserving the angular momentum of the progenitor core, and their intense magnetic fields channel radiation into beams. When these beams sweep past Earth, the neutron star is observed as a pulsar. Pulsars emit radio waves, X-rays or gamma rays, with remarkable regularity, serving as cosmic clocks. Their discovery in the 1960s confirmed that neutron stars are real outcomes of supernova explosions. Some neutron stars possess magnetic fields much stronger than those of typical pulsars, reaching values trillions of times greater than Earth's magnetic field. These objects are known as magnetars. Their magnetic energy can power bursts of high-energy radiation, producing X-ray flares and gamma-ray flashes. The origin of such extreme fields is still debated, but rapid rotation and dynamo processes during collapse may play roles. Magnetars highlight the variety of possible outcomes even within the neutron star category, showing how differences in initial conditions lead to different observable phenomena. If the mass of the core exceeds the limit for neutron star stability, gravity overwhelms all known forces and collapse continues into a black hole. A black hole is an object with a gravitational field so strong that not even light can escape. The boundary beyond which escape is impossible is called the event horizon. The formation of black holes in supernovae may occur directly if the explosion fails, or indirectly if the explosion succeeds only partially, and significant fallback accretes onto the core. Observational evidence for such outcomes comes from both theoretical predictions and the absence of visible remnants in some supernovae. For example, long-term monitoring of massive stars in nearby galaxies has revealed cases where stars appear to vanish without a bright explosion, consistent with direct collapse to a black hole. Supernova remnants, the expanding shells of gas left behind, often provide clues to the nature of the compact object. In some remnants, a central pulsar or magnetar is visible, emitting beams or bursts of radiation. In others, X-ray or radio observations reveal a compact source consistent with the neutron star. In still others, no central object is detected, suggesting that a black hole may reside there, hidden from view. The Crab Nebula, the remnant of a supernova observed in 1054, contains a pulsar at its center that powers bright emission across the spectrum. By contrast, the remnant of SN 1987A has so far revealed no obvious compact object, leaving open the question of whether a neutron star or black hole formed. The properties of compact remnants are shaped by the asymmetries of the explosion. Many neutron stars are observed to move through space at velocities of hundreds of kilometers per second, far higher than their progenitor stars. These kicks arise from asymmetrical ejection of material or from anisotropies in neutrino emission. As a result, neutron stars can be displaced far from the centers of their remnants. In some cases, runaway pulsars have been traced back to their origins, providing direct evidence of these kicks. Over time, neutron stars and black holes interact with their environments in different ways. Pulsars lose rotational energy, powering winds of particles that inflate pulsar wind nebulae. Magnetars produce episodic bursts that can alter their surroundings. Black holes, if in binary systems, can accrete material from a companion producing X-ray binaries. These accreting systems reveal black holes through their strong X-ray emission and orbital dynamics. Each type of compact remnant continues to shape its environment long after the supernova explosion. The study of compact objects also provides insight into fundamental physics. The interior structure of neutron stars depends on the equation of state of dense nuclear matter, which remains uncertain. Observations of neutron star masses and radii constrain possible models. Recent detections of gravitational waves from neutron star mergers add further information as the waveform encodes how matter responds to extreme compression. Magnetaires challenge theories of magnetic field generation, while black holes test general relativity and the strong field regime. In this way, supernova remnants become laboratories for physics beyond the reach of terrestrial experiments. The transition from supernova to remnant highlights the continuity of stellar evolution. A star spends millions of years fusing elements, then collapses in seconds, and finally leaves behind an object that may persist for billions of years. The explosion disperses heavy elements into the galaxy, while the compact core remains as a neutron star or black hole. Both outcomes are essential. One enriches the interstellar medium, and the other provides a site to study extreme physics. Remnants also contribute to cosmic ray acceleration. The shocks driven by expanding ejecta accelerate particles to relativistic energies, contributing to the cosmic ray population that fills the galaxy. Pulsar wind nebulae further accelerate electrons and positrons, adding to the high-energy environment of the interstellar medium. These processes demonstrate how compact objects continue to influence galactic ecosystems long after the initial explosion. From a broad perspective, the existence of neutron stars, magnetars, and black holes as the natural endpoints of supernovae underscores the power of gravitational collapse. Where fusion once supported the star, only degeneracy pressure or general relativity remains. The properties of these remnants, their masses, spins, and magnetic fields record the history of the star and the dynamics of its death. Observations across the electromagnetic spectrum combined with gravitational wave detections continue to refine understanding of how compact objects form and evolve. Supernovae are not a single phenomenon, but a family of events with distinct characteristics that reflect the diversity of stellar progenitors and explosion mechanisms. Astronomers classify them into several main types based on observational signatures, particularly their spectra and light curves. The simplest division is between supernovae that display hydrogen in their spectra and those that do not. This distinction corresponds broadly to whether the progenitor star retained its hydrogen envelope at the time of explosion. From this starting point, further subdivisions capture the variety of outcomes that occur across the universe. Type 2, supernovae are defined by the presence of hydrogen lines. They originate from stars that still have substantial hydrogen envelopes when they collapse, Within this group, Type 2p supernovae show the plateau-shaped light curve caused by hydrogen recombination, while Type 2l events decline more linearly in brightness, suggesting smaller hydrogen masses. Type 10 supernovae and other subclass display narrow emission lines produced by interaction between the ejector and dense circumstellar material. These indicate that the progenitor underwent heavy mass loss shortly before explosion surrounding itself with gas that the supernova shock later illuminates. Such interactions can sustain brightness for long periods and produce unusual spectral features. Type Ib and Type Ik supernovae lack hydrogen lines having originated from progenitors that lost their outer envelopes. Type Ib events still show helium lines, while Type Ik supernovae do not, indicating more extensive stripping. These stripped envelope explosions are often associated with Wolf-Rayet progenitors or with binary interactions that remove outer layers. Some Type-Ik supernovae are unusually energetic and broad-lined, expanding at extreme velocities. These are sometimes linked to long-duration gamma-ray bursts, making them some of the most energetic explosions known. The connection between gamma-ray bursts and certain supernovae demonstrates how diversity extends not only to spectral features, but also to the physical mechanisms that accompany the explosion. Type Ea supernovae, distinct from the core collapse family, are thermonuclear explosions of white dwarfs. They are identified by strong silicon absorption lines near maximum light and the absence of hydrogen and helium. Their uniformity makes them valuable for cosmological distance measurements, yet even within this class variations exist. Some Type Ia events are overluminous, possibly from mergers that exceed the Chandrasekhar mass. Others are underluminous, such as the Type Iax subclass, thought to result from incomplete disruptions where part of the white dwarf survives. The variety reflects different ignition conditions, accretion histories, or merger scenarios. Beyond these main categories, astronomers recognize rare types that push the boundaries of classification. Superluminous supernovae, more than 10 times as bright as ordinary ones, may be powered by interaction with circumstellar material, the spin-down of a newborn magnetar or pair instability explosions in very massive stars. Pair instability supernovae occur when extremely massive stars exceeding about 100 solar masses reach conditions where gamma rays in the core create electron-positron pairs. This reduces pressure support, leading to runaway fusion that completely disrupts the star without leaving a remnant. Such events are thought to have been more common in the early universe when massive metal-poor stars were abundant. Another rare category involves fullback supernovae. In these, the initial explosion is weak and much of the material falls back onto the core, possibly forming a black hole. The observed brightness is lower, and the ejector mass is smaller than in typical explosions. These events blur the boundary between successful explosions and failed ones, reminding researchers that not every core collapse produces the same outcome. The classification of supernovae relies on spectra obtained near maximum light, but the diversity of progenitors and environments means that no system of categories is entirely complete. Continuous surveys reveal new transients that challenge existing definitions, prompting refinements and the creation of new subclasses. This evolving taxonomy reflects the complexity of stellar evolution and the multiple pathways by which stars end their lives. Statistical studies of supernova types across different galaxies reveal patterns linked to stellar populations. Type 2 supernova are common in star-forming regions where massive stars are abundant. Stripped envelope supernova also appear in such environments, but are less frequent, consistent with the idea that only some stars lose their envelopes through winds or binaries. Type Ea supernovae occur in both young and old populations, reflecting the long delay times possible between star formation and white dwarf detonation. The relative rates of these types help constrain models of stellar evolution, binary interactions, and chemical enrichment. The diversity of supernovae has direct implications for cosmology and galactic evolution. For example, understanding whether Type Ia explosions come from single degenerate or double degenerate systems affects how reliable they are as distance indicators. Similarly, quantifying the contributions of different core collapse types helps explain the observed chemical abundances of elements in galaxies. Diversity is not a complication to be ignored, but a source of information about the multiple roles supernovae play in the cosmos. Polarization studies confirm that many supernovae are asymmetric even within the same type. This indicates that classification based solely on spectra and light curves does not capture the full complexity of explosion geometry. Multi-wavelength observations reveal further differences. Some events produce strong radio emission from circumstellar interaction, while others are radio quiet. Some show X-ray afterglows while others do not. These variations suggest that even within a single subclass, a wide range of environments and progenitor properties exist. The recognition of diversity has driven theoretical models to broaden. No single mechanism can explain all types of supernovae. Instead, models must account for the interplay of mass metallicity, rotation binarity, and environment. Simulations explore how each factor shifts the balance between hydrogen-rich and hydrogen-poor outcomes, how it affects explosion strength, and how it influences the formation of remnants. By comparing simulated light curves and spectra to observed ones, researchers refine their understanding of which conditions lead to which subclasses. Supernova diversity also challenges observational strategies. Surveys must be capable of detecting both common and rare events, some of which are faint, fast, or highly unusual. The rise of wide-field high-cadence surveys has revealed many such transients, expanding the known parameter space of supernova behavior. Each new discovery pushes the limits of classification, reminding astronomers that nature does not always follow neat categories. Despite this complexity, classification remains a useful framework. By grouping supernovae based on observable features, astronomers can organize their study and connect specific types to progenitors and mechanisms. The diversity of outcomes is not noise but signal, reflecting the range of physical conditions that stars experience at the ends of their lives. The continuing refinement of supernova taxonomy is therefore an essential part of advancing both observational and theoretical astrophysics. Supernovae are not only remarkable in themselves, but also play central roles in the broader life cycles of galaxies and in the tools astronomers use to measure the universe. When a star explodes, it does more than disperse its own matter. It injects energy, momentum, and newly formed elements into the interstellar medium. This process, known as feedback, regulates how galaxies evolve by heating gas-driving turbulence and sometimes expelling material into intergalactic space. Without such feedback, gas in galaxies would cool and collapse too rapidly, producing stars at rates inconsistent with what is observed. By stirring and enriching the interstellar medium, supernovae act as agents of balance, shaping the pace and chemistry of star formation. In regions of active star formation, multiple massive stars can explode in relatively quick succession. Their combined shock waves merge into superbubbles cavities of hot, low-density gas surrounded by shells of cooler material. These superbubbles can break out of the galactic disk, venting gas into the halo and distributing metals far from the original site of star formation. Observations of nearby galaxies reveal such structures in X-rays and radio, confirming the role of supernova-driven winds in redistributing matter. On smaller scales, supernova remnants compress nearby clouds, sometimes triggering the collapse of dense clumps and initiating new generations of stars. Thus, feedback can both suppress and stimulate star formation, depending on local conditions. Supernovae also accelerate cosmic rays. As the expanding shock waves plow through the interstellar medium, They act as natural particle accelerators, boosting protons and electrons to relativistic speeds. These cosmic rays permeate galaxies, influencing gas dynamics and chemistry. They ionize molecular clouds, affect magnetic fields, and may regulate the formation of stars. Observations of synchrotron radiation from supernova remnants provide evidence of these accelerated particles. Gamma-ray observations further confirm that cosmic rays originate in shocks, as collisions between cosmic rays and interstellar gas produce characteristic gamma-ray emission. Beyond their local effects, supernovae play a key role in the chemical evolution of galaxies. Each explosion enriches the surrounding medium with heavy elements, and over billions of years this enrichment builds up the metallicity of successive generations of stars. Core-collapse supernovae provide oxygen, magnesium, silicon, and calcium, while Type Ia supernovae supply iron and related elements. The relative rates of these explosions over cosmic time determine the abundance ratios seen in stars today. By measuring the chemical compositions of stellar populations, astronomers reconstruct the history of supernova enrichment, and thus the star formation history of galaxies. For example, the ratio of oxygen to iron in old stars reflects the early dominance of core-collapse supernovae, while later contributions from Type Ia explosions reduce this ratio. On cosmological scales, Type Ia supernovae have become essential distance indicators. Their brightness, once corrected for light curve width, is uniform enough to serve as standardizable candles. By measuring the apparent brightness of a Type Ia supernova and comparing it to its intrinsic brightness, astronomers determine its distance. Combining this with redshift measurements yields the expansion rate of the universe at different epochs. This method revealed in the late 1990s that the expansion is accelerating a discovery that introduced the concept of dark energy. To this day, Type Ia supernovae remain one of the most important probes of cosmology, complementing measurements of the cosmic microwave background and large-scale structure. The reliability of Type Ia supernovae as distance indicators depends on understanding their diversity. Although they're broadly uniform, small variations in brightness and color require careful calibration. Dust in host galaxies can obscure and redden the light, complicating distance measurements. Potential differences between progenitor channels may also introduce systematic uncertainties. For this reason, astronomers conduct large surveys of Type Ia supernovae across many environments, seeking to quantify how their properties depend on factors such as host galaxy age, metallicity, and star formation rate. Improving this calibration is crucial for refining measurements of the Hubble constant and the properties of dark energy. Supernovae also define the cosmic distance ladder more generally. Before Type Ia events can be used at cosmological distances, they must be calibrated against nearer distance indicators such as Cepheid variable stars. Observing both Cepheids and supernovae in the same galaxies provides the necessary cross-calibration. In this way, supernovae serve as a bridge between local and cosmological measurements, linking the scale of our galaxy to the size of the observable universe. On galactic scales, feedback from supernovae helps explain why galaxies have the structures they do. Simulations of galaxy formation that exclude supernova feedback produce too many stars and fail to match observed galaxy properties. Including the effects of repeated explosions, however, yields galaxies with realistic star formation rates, gas distributions, and metallicity gradients. This illustrates how events occurring on the scale of individual stars accumulate to shape entire galaxies over billions of years. Observations of galactic winds in starburst galaxies provide further evidence of supernova feedback on large scales. These winds, carrying gas enriched with heavy elements, are driven by the combined energy of many supernovae and stellar winds. They transport material out of galaxies, reducing the fuel for future star formation and enriching the intergalactic medium. The chemical fingerprints of these winds are detectable in absorption lines against background quasars, showing that supernovae contribute to metal enrichment far beyond the galaxies where they occur. The interplay between supernova feedback and star formation is complex. In some cases, shock waves compress clouds and trigger starbirth, while in others, heating and turbulence suppress it. The balance depends on the density of the interstellar medium, the clustering of massive stars, and the overall environment of the galaxy. Modern simulations attempt to capture these processes with increasing detail, guided by observations of supernova remnants, superbubbles, and galactic winds. The outcome is a dynamic picture of galaxies where supernovae act as both regulators and catalysts of change. The importance of supernovae in cosmology and galaxy evolution underscores how local and global scales are connected. A single explosion affects its immediate environment, but the cumulative effect of many explosions determines the chemical composition of galaxies, the regulation of star formation, the propagation of cosmic rays, and even the measurement of the universe's expansion. In this sense, supernovae are not isolated events, but integral parts of the cosmic ecosystem. By studying them, astronomers gain insight not only into the fate of individual stars, but also into the structure and history of the universe itself. The study of supernovae is enriched by historical records, and by a few particularly important modern events that serve as benchmarks for astrophysics. Long before telescopes, ancient observers documented the sudden appearance of bright new stars in the sky, some visible even in daylight. These records, preserved in Chinese, Japanese, Korean, Arabic, and European chronicles, provide valuable data about past supernovae. One of the most famous is the event of 1054, recorded by Chinese astronomers, which produced a star so bright it was visible in daytime for weeks. The remnant of this explosion, the Crab Nebula, still expands today and contains a rapidly spinning neutron star at its center. The connection between the ancient record and the modern remnant provides direct evidence that historical guest stars were indeed supernovae. Earlier still records exist of bright transient stars in 195, 393 and 1006. The event of 1006 is considered the brightest stellar event in recorded history seen across much of the world and described as casting shadows at night. The remnants of these explosions are now studied with modern instruments, revealing expanding shells of gas that match the locations of the ancient sightings. Such correlations demonstrate how cultural history and modern science intersect with past observations, providing data for present astrophysics. In the era of telescopes, supernova research expanded dramatically. In 1572, Tycho Brahe observed a bright new star that challenged the prevailing belief in an unchanging heaven. Careful measurements showed that it had no detectable parallax, proving it was far beyond the planets. In 1604, Johannes Kepler recorded another such event. The remnants of both Tycho's and Kepler's supernovae remain visible in X-rays and radio, allowing modern astronomers to study the products of explosions that once transformed human understanding of the cosmos. These historical events illustrate how supernovae have long acted as milestones not only in stellar evolution, but also in the history of science. In modern times, one event stands out above all others: SN 1987A. Detected in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, it was the closest supernova observed in nearly 4 centuries. Its discovery allowed astronomers to track a supernova in unprecedented detail across multiple wavelengths. The progenitor was identified as a blue supergiant, challenging the expectation that Type II explosions came from red supergiants. The light curve showed unexpected features, including a slower rise and peculiar spectral evolution. Neutrinos from the core collapse were detected on Earth, confirming theoretical predictions of the role of neutrino emission. Over the years, SN 1987A has become a laboratory for studying nucleosynthesis, shock interaction, dust formation, and remnant evolution. Its expanding rings of gas illuminated by the explosion continue to be observed as the shock interacts with the surrounding material. SN 1987A demonstrated the value of combining multiple forms of observation. Optical, ultraviolet, infrared, X-ray, and gamma-ray data all contributed along with neutrino detections. The event showed how each wavelength reveals different aspects. Optical light traced the overall evolution, infrared revealed dust formation, X-rays mapped shock interactions, and gamma rays confirmed radioactive decay. It remains one of the best-studied astrophysical phenomena and continues to shape models of stellar evolution and explosion physics. Beyond SN 1987A, modern surveys have uncovered thousands of supernovae across the universe. Automated wide-field telescopes scan the sky nightly, capturing transients soon after they appear. These surveys have revealed rare classes such as superluminous supernovae, rapidly declining events and explosions in unusual environments. The diversity uncovered challenges theory and expands understanding of what massive stars and compact remnants can do. With every new survey, the sample of known supernovae grows, enabling statistical studies that link rates and properties to host galaxy types, star formation rates, and cosmic epoch. Supernovae have also become central to cosmology through Type Ia observations. In the late 20th century, two independent teams used distant Type Ia supernovae to measure the expansion history of the universe. Both found that the expansion was accelerating, a result that led to the concept of dark energy and earned the 2011 Nobel Prize in Physics. This discovery illustrates how supernova research transcends stellar astrophysics, informing the most fundamental questions about the fate of the cosmos. Ongoing programs refine these measurements, seeking to reduce uncertainties and test whether dark energy changes over time. The role of supernovae in galaxy evolution, nucleosynthesis, compact object formation, and cosmology makes them central to modern astrophysics. Their study combines observations theory, laboratory experiments, and increasingly multi-messenger approaches. Future detections of gravitational waves and neutrinos from nearby events will provide insights deeper than ever before. Large surveys with next-generation telescopes such as the Vera C. Rubin Observatory will discover supernovae by the tens of thousands, allowing unprecedented mapping of their diversity. Space telescopes will extend observations into the infrared, probing dust formation and high redshift explosions. The anticipation of the next galactic supernova looms large. When it occurs, it will be observed across the electromagnetic spectrum in neutrinos and perhaps in gravitational waves. Instruments around the world stand ready to record every stage from neutrino burst to shock breakout to late-time remnant evolution. Such an event will test every aspect of current models and likely reveal surprises that challenge understanding. The rarity of nearby explosions makes preparation essential, but history assures that one will eventually occur within observational reach. From ancient guest stars recorded by human eyes to modern surveys cataloguing thousands of events, supernovae have remained at the forefront of discovery. They illuminate the life cycles of stars, enrich galaxies with elements, create neutron stars and black holes, accelerate cosmic rays, regulate star formation, and serve as tools for cosmology. Their study connects the smallest scales of nuclear reactions to the larger scales of cosmic expansion. They are at once transient and enduring. Each explosion lasts months, but its consequences shape galaxies for billions of years.